I'm not going to tell you about hacking or penetration testing in a regular sense. I'm more looking at it like, well, if you think about the regular penetration test, you are kind of against the administrators. But if you look at software development area, they need exactly the same skills and same tools in order to fix and find those problems in software development. And it's a huge area of work, actually. Some studies have looked at that they have more than 2% of total development force nowadays with security background or with security expertise. And they are very important people in software development nowadays. So I'm just going to through some of the techniques and how they actually map back to software development lifecycle. So the SDLC stands for software development lifecycle. I have a huge amount of slides. We have very little time, so I'll go very fast and try to do a little bit of demo in between as well. So about me, I've been doing fuzzing since late 90s, so quite some time. I have a university background, and Protos tools, which many people use, at least in the telecom space, are basically a result of that. And commercially, we do exactly the same. So to get to the actual topic, probably the only public secure development lifecycle is published by Microsoft, but all large software companies have their own. So there's different setups of different styles of software development lifecycles and how security is integrated into software development by every single large company, software development company out there. And there's no one single way, but many people use the SDL as the reference, and many of the ideas there are very common. First thing that I will disagree immediately is that fuzzing is not only a testing tool. Many software developers think that, okay, when the software is developed, that's when the security testers come in and start testing the tool. So static analysis is in the implementation and fuzzing is in the testing. But nowadays, it's very hard to find a software development company that doesn't have agile practices or some other ways where testing and development are anyways already interleaved in some way or another. So fuzzing is used and has to be considered in every step in software development lifecycle. Typical fuzzing process is very easy. You just identify what needs to be tested. You generate those test cases, which are very similar to testing like web applications with SQL injection, just on the protocol layers, APIs, interfaces in the whatever software you end up testing. So interfaces are always different, and you always need to do quite complete coverage of all of those interfaces. So first difference between penetration testers. Many penetration testers are happy when they find one bug and exploit it and demonstrate that you can exploit it. Software developers need to find every single bug, but they don't care about exploits. They have no use for any exploits. That's waste of time. You need to find as many problems, and you have to somehow prioritize very quickly which ones are most critical. But exploits, who cares? Everyone in the software industry knows that if they see a register corruption, you say 414141 in any of the registers, it's an exploitable bug. It doesn't need to be proven any further than that. Then running the test, analyzing the results, and looking at how to actually report that to someone who doesn't know what you are doing. So in most of the cases, biggest challenge in security testing is that you are the only one in the software development company who knows what you're doing. And even the results are not understood by programmers. They are not understood by the managers or anyone else. So that's the biggest challenge often in software engineering. So looking at a traditional waterfall process, I've grayed out the implementation part because often in programming you don't really do much testing. That's really the coding part. But that also has changed a little bit with the agile processes. But if you map the fuzzing process into the software development process, you already start analyzing those interfaces during the design phase and requirements test phase. So you have to already be involved very early in the process in basically defining your own test requirements for the end product. Then finally, in the testing, you actually conduct the tests, and in the release phase, you provide some kind of an acceptance gate or plan how the final product is approved to be released. Unfortunately, in real life, the last step is the first phase where fuzzing gets introduced into the software development, and the result is that just 2 weeks before the release, you suddenly find 200 vulnerabilities in the product, and the product release is postponed by 3 or 4 months. And that costs a lot of money for the software development company. Or, as a result, no one ever even fixes those problems because they don't want to postpone the release of the product, which would be a waste of time. So, I have some more detailed examples of what you can do in different phases and what you should look at if you do that. So just ask me if you need the slides. Unfortunately, I will skip through most of these and then just show you how you can actually get started with fuzz testing, fuzzing, and security testing. So we have provided a free tool for FTP fuzzing just for practicing purpose, and you can get them from our website. The username and password should be valid for at least a few days. Even after that, you can just request a new username and password from us. But basically, you can get the full commercial tool for free anytime you need. Then, when you are setting up the test setup, you usually want to run a virtual setup and then want to set up your test targets in virtual hosts, like I will be using in the demo, but you can also just run it on a local host, especially with the FTP setup. So it doesn't really need to be virtual setup. Our tools are completely platform independent, so don't worry if you like Windows. Just 10 minutes, you are all done with the setup. 30 minutes after, you have completed the test. So it's very fast process of finding vulnerabilities in any product. Let's get the test actually running because it will take a while. So what I have is intentionally weak, vulnerable Linux, and I have installed an old version of an FTP server, and I have it running, and it's just showing the log file there. And then I have the exactly same fuzzer that you can download from our website. And only thing I need to do is, you need to configure the target IP. And you can, but you don't need to, also configure the username, password, valid or invalid passwords for the domain so that tests get much deeper penetration into the process. So if you have anonymous access enabled, then that's a good username to use. I'm using a real account. Don't hack my laptop. It doesn't have Wi-Fi. It doesn't have Bluetooth, but that's a real account on this host. And I'm accessing temp because it's really low priority account. It doesn't have any rights on the host. That's all. All you need to configure. Instrumentation is useful because instrumentation means that in between every test, it checks if the target is still up and running, whether it's alive or not. So I'll enable that. And that's it. Everything else is completely automated in fuzzing. Fuzzing is built around industry standard protocols like FTP, like HTTP, TLS, whatever you want to break. If you want to break those load balancers, if you want to break those encryption of loaders, you use different protocols just in order to target those. You can test IP version 6 or IP version 4, whatever protocols your Nmap runs reveal on the test targets, you can then fuzz everything around those. So while it's running, let's get back to the presentation. So basically, really basics of product security. The biggest challenge in product security is that when you have a product released, it already comes out with a predefined set of vulnerabilities. Vulnerabilities are not like emerging and suddenly created when someone finds them, but they are already there, waiting to be found, and eventually all of them, majority of them, will be found. Some of them, it might take 10 years, even 20 years to be found, but they will eventually most probably be found by someone. When someone finds a vulnerability, you get some limited exposure to that. So vendor internal vulnerabilities quite often are never reported externally. Some companies have a policy that even if they find internally found bugs, they will issue advisories, but in real life, majority of software companies will never, ever, ever say that one of the patches actually included updates to problems that they had found internally. So if you look at bug databases, IDS systems, they will never know about these problems because it's secret knowledge. There might be other third parties who know about the same problems, but it's not in their interest either to actually disclose those weaknesses. Because if an underground community, hacker community, criminal enterprise has a set of vulnerabilities, they have no interest in getting those fixed. I recall just recently there was a very critical Linux vulnerability that had been used in zero-day attacks for 4 years before. So the greatest challenge for software developers is that even after the software updates, how many bugs are still remaining and how many new bugs actually were introduced with each and every security update or software update. And for software developers, majority of coders, programmers, testers, this is a security problem. It's not an exploit. It's not getting access to a box. It's not anything else but a crash level issue. Only thing you need to demonstrate to a programmer is a crash level issue, and then go to find more bugs, more issues, because they want to get those fixed. And the more crash level issues you find, or memory leaks, or CPU consumption problems, those are the ones that they are worried about. If you start talking about buffer overflows or SQL injection, they just get confused and they don't understand. But if you show a crash, they will understand and they will fix it. So when you look at product security people, there's a bit different languages used by many of the pen testers, product security people, and software developers. And typically, terms that everyone understands, of course, are vulnerability. What are threats? What are the actual attacks? What are failures? Even there, failure is defined by different people in different ways. What is a failure that actually is interesting for the software developer? Many security researcher colleagues, like everyone knows, like Charlie Miller or such, they don't even become interested in a crash level issue if you don't see that it's exploitable. But if you look at a software developer, if you see a crash level issue, they're actually much more interested in it than something that is exploitable. I even heard people say that, it's not a big issue. Okay, someone owned our router, but it's still up and running. It's making money. But if you crash it, that costs money. So it's a completely different mindset for the many people. So I hope everyone, okay, let's ask it a little bit differently. Who doesn't know what fuzzing is? Everyone knows. You are scared to admit. Anyways, there's two different ways of doing fuzzing. Fuzzing is basically crash testing software. It's just sending lots of garbage in and expecting garbage out. There's two different ways of doing fuzzing, and the other one is doing template-based fuzzing, and the other one is specification-based fuzzing. And the biggest difference is that in template-based fuzzing, you take a seed of some kind, like a traffic capture from network, a set of files, JPEGs, document formats, and then with any potential algorithms that you are using, you start mutating those bit by bit or byte by byte, and or however advanced methods you want to use. Specification-based fuzzers, on the other hand, build an entire model of those communication interfaces, often actually take those models from R&D directly, work together with the R&D in order to build those models for the interface. And then they get full coverage of that interface because they actually have inside knowledge of how that works. Major difference is that if you look at it as a traditional pen tester, the template-based fuzzing seems much more interesting because it's a general purpose way of doing fuzzing. You only need one tool and you can fuzz anything. Specification-based fuzzing is interesting if you mostly play with one playground. If you only do voice of IP pen tests, then you're only interested in a handful of protocols. If you do only web application testing, you don't really need anything else but like IP version 4, 6, then SSL, TLS, HTTP, sometimes XML, and some other application languages. But you get much better test coverage with the specification-based fuzzers. In some studies, it was like compared that mutation, template-based mutation fuzzers have like maybe 10% bug coverage, so they find about 10% of the bugs in hiding in software, and specification-based fuzzers can reach up to 80% coverage rate, so they find majority of the bugs. Of course, no technique alone finds everyone. If you combine different techniques, you find a much more complete set. Anyways, getting up your own test setup running, the easiest way is, of course, building a virtual test setup, because then it gives you full control of what you actually can do in the test environment. So in my setup, I have currently only one virtual host running, and I am monitoring it on the master computer, and the fuzzer is also running on this. So what you can expect on a low power computer anyways. So in this setup, I have, like I showed, one Linux host running as a target, and the actual fuzzer is running on the Mac. When you build your own practice ground, it's often best to choose either known bad products, like just going to a website and not taking the latest version of an FTP server, just going 2 versions back and building a known vulnerable setup that you can use as a playground for your fuzzing practices. The other way is that you just go to SourceForge and take any open source project related to that protocol, because those are typically the lowest quality products. So open source doesn't guarantee good quality. Everyone knows that. So you just take any one out there and just try it out, and most probably you will find a lot of different security problems, because face it, there's probably only 2 users for that project anyways out there. So it's not being tested even by users. Then you install those targets on your hosts, and then you get them running. This is just a simple setup how I installed the WZ FTP daemon, and then that's it. You are done. Your test setup is ready and running. A special setting, when you look at it from pen testing perspective, is often that you don't actually necessarily trust on the specifications developers give you or your customer gives you. You want to actually map that attack surface yourself. It's not a necessary step always, but it's an interesting step, and everyone probably knows how to run like Nmap and such. But let's look at a different way of doing it. So when you do a pen test of a device or of a network, just using Nmap-like tools, you don't actually see everything in the network. You very rarely see the client-side implementations in the network. You don't see the web clients. You don't see all the like DHCP clients on the hosts. You only see the server-side implementations. And if you want to map everything on the network, you just need to get a lot of recording points, and you need to start mapping all the traffic that is actually really happening in the network. So that will actually automatically give you an attack surface analysis for the device or for the network, exposing both client-side implementations and server-side implementations, and also the attack vectors that are open and exposed and actively used in that device. An example of that in this test environment is, of course, running on the master host. A sniffer, like in VMware, you can see everything inside that virtual net. easily. You don't just use their own tools to do that. You can see all the VLANs and everything in there, and you can see all the communications, record everything, and see what's really happening. And as a result, you will then get an automated map of the network, showing all the IP entities, the actual communication interfaces between every single device. You can use Google Maps like systems to map those in geographically, so you can see the real external interfaces to the system and to the network as well. You can map the protocols and such and so on and so on. There's many tools for doing this. This is just our tool for doing it, but there's many other similar techniques. And that will help a lot in prioritizing your fuzz testing then, whether it's in a pen test or whether it's in QA, quality assurance. The fuzzing process itself is very straightforward then. Like I showed, you just set it up and hit play button and you are started. Many of the fuzzing tools are command line tools, so basically you just give the parameters where the host is. Sometimes you need to give them a seed value if they use random fuzzing, but most of them actually have a very optimized set of tests that they will run. Some of them create huge amount of text-based log files, which you just then have to grab and try to find those error messages from. Some of them create Excel sheets and visualizations on where the problems are, and you have to actually work your own mechanism how to actually detect those flaws that your customer wants you to find. So if you're working in an R&D where performance is optional, really critical for the product, you have to have process monitors in place. You have to collect data on how much CPU power each one of those test cases generated. Sometimes you often see like amplification attack capabilities that you send a packet and you can actually direct the return to somewhere else. And detecting those requires, of course, different monitoring tools, different instrumentation. So the monitoring toolkit is usually something that you build based on the test environment. Results then can be everything from crashes to like performance-related issues, so that the system becomes unresponsive, very slow in responding to these requests. Let's see what really happened here in the test actually during this time. So it's run about half of the tests. It hasn't crashed any times yet. You can see it from here, failed 0 times. But there's other verdicts quite many times, which often means that there are some issues in processing those requests. And in this case, majority of those requests, what they actually create is like a slow response. It takes 2 seconds to recover from the actual test case, and then it doesn't get back into operational form after that. So for example, here we can see that typical test cases take like less than a second to execute, and then suddenly some of these take 300 seconds, 600 seconds, 16 seconds, whatever threshold you want to set for the performance in your test setup. Template-based fuzzer is much more straightforward actually, or depends how you look at it. Only thing you need to do is get a PCAP of something, load it into a mutation fuzzer, give it an IP address, and everything else is actually pre-configured in the capture. So it's really like capture, replay, mutate combination. Very straightforward, but like I said, test coverage is much less. Traffic capture fuzzer is still also surprisingly efficient. So I prepared this demo quite some time ago, but while I was setting it up, I actually ended up listening to my Mac and my Linux. They, for some reason, started talking to each other. I looked at what is that happening, and there was a Samba server running on the Linux, and you know Samba likes to talk to every other Samba in the network. So I captured that and just loaded into a traffic capture fuzzer, and it only took a few test cases, and the Samba crashed. So just getting simple traffic captures from the setup where you are at, you can, in a matter of minutes, already find critical flaws in critical systems in that specific device or network. I'm not showing the details of that because we haven't had time to talk to Samba team yet. Then when you look at the entire attack surface of a device, in this case, these are all Wi-Fi access points. This is not even like a full attack surface coverage of the systems, but every access point, AP1 to up to 7, were tested on a number of different protocols. NA here means that it wasn't tested, but test results were very, very different between all of these devices. Many of them shared very similar hardware, many of them shared very similar operating system, and even like similar web servers and so on, but test results, no matter what they were actually using, were almost always different from each other. And the reason is, of course, very understandable. It's not enough to test like Apache web server once. People tend to build it with different options, different plugins, for different architectures, and all of those impact the actual test execution results. So it's still always important to run all the different protocol layers just to verify that there's none of these low-hanging fruits out there to be found by hackers. And the most critical aspect of fuzzers is really looking at the coverage aspect. So how well do you actually cover all that attack surface that you find? So you can divide coverage in two different aspects. The other one is precision, which means that how well you actually understand that specific protocol interface. Are you testing all the different sequences that are specified in that, all the messages, all the structures? And then the accuracy is more about the different anomalies you use. It's almost useless to run SQL injection anomalies against a voice over IP application, unless, of course, if you have a back-end database processing all those usernames in telecom setup as well, which it usually just happens to be. So exactly the same type of anomalies are applicable across different industries. They are not only web application vulnerabilities. The same bugs exist in mobile applications, in voice over IP applications, whatever applications you think of. And the more anomalies you have, the more test cases you end up having. So when you look at an integer anomaly, just really like QA people would call it boundary value condition. So you have a defined set of values that can be given to a number, basically. If you want to try all 8-bit numbers, it already is more than 200 test cases. If you want to go through all 16-bit numbers, you end up generating more than 60,000 test cases just for one single value in that protocol specification. So the more values you want to try, the more test cases you end up generating with your process as well. So you have to do compromises in the test execution, because unfortunately in development, in QA, you are not paid by hour. So you're actually much more better rewarded if you can do a very quick job at it. So you very rarely have more than a day, 2 days, to do a full test of the device. And actually, the more faster you do it, better coverage you do in a shorter time frame, that's really the metric of efficiency for the security testing. So you have to choose between running a lot of test cases and between running less test cases, but much, much more optimized test cases. And one solution for that is, of course, that most fuzzers are software. Almost every single piece of fuzzing tools which you find from OWASP or from wherever you look for, they are all software-based components. They are very easy to run in parallel. They are very easy to run on high-performance platform. Today, hardware doesn't cost almost anything. So compared to running those tools on your laptop, like my Mac, you often actually end up buying high-end server components and run those extremely fast. So looking at some of the tests that, for example, we were doing, you can easily run more than 40,000 test cases per second if you are testing a UDP interface. And even with TCP-based interfaces, like HTTP protocol, you end up running tens of thousands of test cases per second. And even if you have millions and millions of test cases, you can still run those rather quickly. Another aspect of performance is that remember I said that many hackers actually are more interested about exploitable problems. But when you show graphs like this to a QA guy, where you compare a steady, legal, normal traffic and the load it generates, and the same volume of traffic but with anomalous inputs, and suddenly generating 100 times more CPU consumption, it will trigger a lot of flags in the product management and everywhere. Because even a security guy will immediately see that this is like the secret source for DOS, distributed denial of service attacks. If you find a magic input that actually causes 100 times more processing in the target than a valid request, then you don't need that many attack threats anymore to actually drive it down. So even if it's not a crash level issue, even if it's not like an exploitable bug, it is something that hackers, if they know what they do, will find out and can exploit. And QA teams actually want to stay ahead and want to find these much faster than what hackers do. We've tried to cover many of the aspects of fuzzing in a book, which you can find. Unfortunately, it's written by, published by an academic publisher, so it's not like one of the cheapest books. But if you are interested, we can give a few free copies. Just drop me a business card and I'll do a lottery or something. It's written by two ex-NSA hackers, Jared DeMott, Charlie Miller. Many of you might recognize Charlie Miller from iPhone hacks and all that. And it's really aimed at both security people, software developers, testers, in finding those problems and building fuzzing into software development and not using it after release of the software. With that, thank you very much for your attending. Any questions?